Hi everyone. This video will introduce us to the solubility product, which as you can see is very closely related to the fourth goal in our class. And just a little bit about the solubility product. It tells us the extent that a salt dissolves. And that might not sound too exciting, but it just depends on the salt. For example, if you have mercury 2 sulfide, HGS, this is found in the Earth's crust, and it's also known as cinnabar, and it's not very soluble, but in water it does dissociate into mercury 2 and sulfide. And since mercury 2 is toxic, now I'm really interested in the extent that this salt dissolves because it produces toxic ions. Now the value of Ksp for cinnabar is very small. It's 5 times 10 to the negative 54th, meaning that this equilibrium lies to the left. And that's going to be true for all Ksp values. Ksp values are all much, much less than 1. These equilibria lie to the left. And just as a reminder, let's write the Ksp expression for cinnabar. It'll just be products over reactants, but because the reactant is a solid, we don't include it. So Ksp will simply be the concentration of mercury 2 times the concentration of sulfide. We can also define the solubility of a salt as the amount that dissolves per volume of solution, so we can use units like molarity or milligrams per liter. It just depends on how the question is asked. So let's try to do an example. Let's see if we can calculate the solubility in units of molarity of silver chromate. They gave us the formula weight in case we need it, and half a liter of deionized water, and they gave us the solubility product of silver chromate. So the very first thing that I want to do is write down the chemical reaction that takes place. Silver chromate is in equilibrium with 2 moles of silver and 1 mole of chromate. If you don't write this reaction, you may miss this subtle step that for every 1 mole of salt, there are 2 moles of silver. And then from here, since we're just getting started, I might want to make an ice table. And you may remember making these ice tables in general chemistry where I stands for initial, the C is for change, and the E is for equilibrium. And I'm also, just to be very clear, I'm going to sketch our initial conditions. So this is a lab bench, and we might have a jar of silver chromate, solid, and then beside it we might have a beaker of deionized water. How would you describe the initial conditions? Well, do you have any silver ions in this beaker? No. Do you have any chromate ions in this beaker? No. That's because you haven't done anything. That's the initial condition. So for silver chromate, I really don't have to put anything there, but I usually just write the word solid just to put something there. So now the change is when something actually happens. This is when we pour a little bit of the salt into our beaker of water. So some of it dissolves, we don't know how much, it goes down by X, and ions are produced. And again, because you have this coefficient here, the moles of silver are going to go up by 2X, and chromate is just going to go up by X. So at equilibrium, we'd have 2X for the concentration of silver and X for the concentration of chromate. And it really doesn't matter what you put there for silver chromate because it's not involved in the Ksp expression. So this is, I think, the most important part of the problem, setting it up. I think from here, it's all downhill. Let's write our Ksp expression. Ksp is going to be the concentration of silver squared, so that'll be 2x the quantity squared times the concentration of chromate, that'll be x. So if we do the algebra here, 2x squared is 4x squared times x, that's 4x cubed. And if we rearrange for x, I think that'll be the cube root of Ksp, which is 1.2 times 10 to the negative 12th over 4. And when I did the arithmetic, I got 6.6 with an insignificant 9 times 10 to the negative 5th molar. Now, is that the solubility? Well, it's X, and we can see that X is the chromate concentration at equilibrium. If we double it, that's the silver concentration at equilibrium. But yes, it is also, in fact, the amount of salt that dissolves per volume of solution. So yes, this is the solubility. Now, don't panic because you haven't used your formula weight or this volume. It just depends on how the question is asked. I think in class, maybe we'll do an example where you would need to use the formula weight or this volume. So that was just hopefully a review of the KSP. I hope it brought back some good memories, and thanks for listening.